Hello everyone, I'm Fan Hong from Tsinghua University. I'm glad to present our recent work in multi-threaded program verification. The title is Interference Relation Guided SMT Solving for Multi-Threaded Program Verification. The verification on multi-threaded programs is complicated because of the vast number of thread interference. Consider the example program with two child threads and a main thread. We have the safety property that m and n are not equal to 0. Because of thread interference, there are 6 possible executions. No matter in which situation, the assertion is held, so the property is guaranteed. We say this multi-threaded program is correct. However, too many possible executions make it difficult to verify such program. Satisfiability modulus theories is widely applied in program verification. An SMT-based program verifier consists of 2 components, a front end that encodes the program into a verification condition formula, and a back end that calls the SMT solvers to solve this SMT formula. In SMT solving, unassigned variables need to be decided to check the satisfiability of the SMT formula. So, a reasonable decision order of unassigned variables can drive the search direction of the SMT solving and significantly affect the SMT solving efficiency. So, in this paper, we outline the interference relation in multi-threaded program and develop a strategy to guide the SMT solving for multi-threaded program verification. We show that the interference is important, and we recognize the interference variable and generate a decision order to improve the overall efficiency. So first, we want to introduce how to model a multi-threaded program. Consider the example program, which contains a main thread and 2 child threads. One of the most efficient ways for modeling a multi-threaded program is using partial order. One can model and analyze the execution order of memory access events to represent the possible program executions. An event E is a read or write memory access. We denote clock E as its time step. So first, the program order constraint. Consider the access event occur in each thread, so we can obtain a chain of program order constraint. The program order constraint follows the natural order of the instructions. So for simplification, we create an event order graph whose nodes are access events, and the edge between 2 nodes are the order constraint between access events. So we color green to represent the event is a read event, and we color blue to represent the event is a write event. So we can get a chain of program order constraint. Moreover, because of thread interference, a read event may read its value from many possible write events that access the same memory address. So we call this constraint read from constraint. Okay, for the read event x3 in the example program, we can see there are 2 possible write events that x3 may read from, that is x1 and x2. Then we have 2 read from constraints, one from x1 to x3, and the second is x2 to x3. So we use a Boolean variable named the read from variable to indicate that a read from constraint hold. For the read from constraint between x1 and x3, we know that this Boolean variable implies x1 happens before x3, and the value obtained by x3 is written by x1. So we have the read from constraints. Moreover, the write serialization constraint captures the total order between the write event to the sim variable. So for example, consider the two write events of namely x1 and x2. So either x1 is overwritten by x2 or x2 is overwritten by x1. So we have two WS constraints from x1 to x2 and from x2 to x1. Also, we use a WS variable to indicate that a WS constraint holds. So for two write events of the same variable x, there must be one that overwrites another. Moreover, a read event can only read from the latest write event to the same memory address. So here we use the write events y1, y4, and the read event y3 as an example. If y3 reads from y1, so there is a read from constraint from y1 to y3. And if y4 overwrites y1, there's a WS constraint from y1 to y4. Then we know that y3 must happen before y4. Otherwise, if y4 happens before y3, when y3 is executed, y4 already overwrites y1, then by no means can y3 read from y1. So such constraints are called from-read constraint. It is implied by a read-from constraint and a WS constraint. Besides the ordering constraint, we also encode the value assignment constraint of the example program into file SSA. So consider the example program. We have the following value assignment constraint. Moreover, for the safety property, we encode the error condition for error. It is the negation of the property. That is, M3 is equal to 0 and N3 is equal to 0. So finally, for the example program, we can obtain its verification condition formula. It is the conjunction of the above subformulas. So the program is correct with respect to the given property if the verification condition formula is unsatisfiable. And in SMT solving, we need to decide those many unassigned variables and check whether the formula is satisfiable. So in multi-threaded program, two accesses interfere if they access the same variable and at least one of them is a write access. So among the constraints, we have the interference constraint, that is the read from constraint, write serialization constraint, and the from read constraint. They capture the semantic of thread interference, and this is special for multi-threaded program than the sequential program. So in SMT solving, there are four kinds of Boolean variables. That is, SSA variable, which represents the program statement. We call those variable VSSA, and order variable, which represents the order between the clock variables. For example, clock x1 is lower than clock x3 means x1 happens before x3. So we call such variable the ordering variable. Moreover, we have the read from variables and the write serialization variables, which implies the read from relation and the WS relation. So among those four kinds of variables, we call the read from variable and the write serialization variable the interference variable. And the interference relation is important. So a symbolic concurrent execution is a partial assignment that assigns value to part of variables in interference variable. A symbolic concurrent execution is valid if and only if there exists a total order among the events. That is, the corresponding event order graph contains no cycle. Otherwise, the corresponding event order graph contains at least one cycle, so an event happens before itself, which is impossible in actual program execution. Note that we use clock to denote the occurrence of an event. So in integer theory, A cycle in event order graph means integer is lower than itself, as there is no total order among the events, which is also impossible. So interference relation is important in multi-threaded program. If a cycle occurs, there must be some interference variable from which this cycle can be derived. That is, the cycle is often caused by interference relation. So consider the first graph. We know that the read-from relation between the write event x2 to read event x3 and the read-from constraint from the write event y4 to the read event y2 is decided. Then there is a cycle between y2, x2, and x3, y4, and y2. So this cycle means the current decision of the interference variable is impossible in actual program execution. And again, the second graph is another situation where the cycle is caused by the from-read constraint. Also, from-read constraint is implied by read-from and write serialization constraint. So, we know that in multi-threaded program verification, the interference relation is important, and it is implied by interference variable. So, in SMT solving, the traditional approach is basically a depth-first search procedure. It may assign a value to an unassigned variable to some extent randomly. So the SMT solving is unaware of that interference relation is important. However, prioritizing interference relation in SMT solving can help SMT solver quickly decide whether the current assignment leads to an invalid execution or not. Therefore, interference relation is important, and however, SMT solving is unaware of this, so we want to prioritize the interference variable. So we generate a decision order to decide which unassigned variable should be selected. So we propose 4 heuristics. First, interference variable a priori to other variables. That is, for 2 variables, one is interference variable and another is not interference variable. We say interference variable has a higher priority. This is a basic heuristic. Then there are 2 kinds of interference variables, that is, the read-from variables and the write serialization variables. It can be obviously observed that read-from variables can not only dominate the order of memory access events, it can also determine some valuations of program statement variables in VSSA. So, well, WS variable cannot do this. And secondly, many WS variables implies the WS order, and the WS order are implied by program order. Boolean variable for representing those WS order can thus be directly propagated during estimate solving. So therefore, we suggest giving the read-from variables higher priority than the write serialization variables. Additionally, a read-from variable links a read event and a write event that access the same memory address. If there's 2 events belong to the same thread, we call the read-from relation internal. Otherwise, it is external. If the write event and the read event are from the same thread, this read-from relation is also implied by the program order and has nothing to do with the interleaving semantic of a multi-threaded program. Instead, if the read event and the write event are from different threads, this read-from order captures the thread interference relation and reduces the uncertainties caused by thread interleaving. So the reason why a multi-threaded program are error-prone is thread interference. Therefore, we suggest to giving higher priority to external read-from variables than internal read-from variables. And finally, thread interference causes that the value obtained by a read event may come from many possible write events. The more writes to a shared variable, the greater impact of the thread interference on this variable. So for a read from variable we use write v be the number of write event that the read event may read from. So for two read from variables v1 and v2, if write v1 is greater than write v2, we say uh, thread interference has greater impact on v1 than v2. Therefore, we assign v1 a higher priority than v2. When when the SMT solving selects the next unassigned variables, we use this decision order and forces it to select the interference variable firstly and perform the constraint solving. So here is our interference relation guided SMT solving framework. Okay, first, for the input formula, I input SMT formula. The SMT solver first perform propagation and check whether there's conflict in the current formula. If there's no conflict, it will choose the next unassigned variable and continue to perform the constraint solving to check whether the current formula is satisfiable or not. So we convey the decision order generated using our heuristics to the estimate solver. When the estimate solver needs to choose the next unassigned variables, we force it to choose the interference variable firstly. So the estimate solver will assign the value to a selected interference variable and continue to perform propagation and check to find if there's any conflict. If conflict is found, it needs to resolve conflict and backtrack to reverse some value of assigned variables. If there's no conflict, it continues to choose the next unassigned interference variable following our heuristic. So if all the interference variables are decided or propagated, we let the estimate solver to choose the next unassigned variable from other variables than interference variable. So in this paper, we recognize the interference variable and elaborate a decision order to guide the SMT solving. A DPLLT is a basic framework for SMT solving. Okay, the next is our evaluation. So we implemented our approach on top of CBMC and Z3. Our tool is called ZPRE. CBMC is a bounded model checker for C program. So we recognize the interference variable when encoding the verification condition formula. We name the interference variable with a special fashion. We record the thread information and the thread and the program location. And in SMT solving, our tool ZPRE can recognize the interference variable, and to generate this decision order. So we compare ZPRE with several with Z3 under different memory models, the sequential consistency memory model and the two-week memory models. 1061 C program writing in using the pthread library. So those benchmarks are collected from the software verification computation and in their concurrency safety category. So first, we encode those program into their verification condition formula under different memory models, and we compare our tool Z3 with the uh, traditional Z3 under those three different memory models. The following figures show is our the overall results. Each point under the diagonal represents a case where our method performs better than Z3. Those figures show that in most cases, especially in complex programs, our interference relation guided SMT solving can achieve higher efficiency. So Table 1 summarizes the experimental results. Uh, our approach solves small cases and is faster than A3. And we also list many other statistics about the decision propagations and the conflict in SMT solving. This data also shows that our method can reduce the search procedure and consume the less memory. So we think that the interference relation guided approach for multi-threaded program verification is useful and it is work. So here is a conclusion. In this paper, we first introduced the partial order-based symbolic encoding to show how to encode a multi-threaded program into its verification condition formula. And in SMT solving, there are many unassigned variables need to be decided and check the satisfiability of the formula. So among those variables, we see that interference relation is important and it is implied by interference variables. So we want to prioritize interference variable in SMT solving. So compared to the traditional SMT solving, we propose an interference relation guided SMT solving framework. We generate a decision order using our heuristics to force the SMT solver to choose the interference variable firstly and it may affect the search space of the SMT solving since interference relation dominate many relations. So compared to the random search, this strategy is work in multi-threaded program verification, and we implemented our approach on top of CBMC and Z3. The experimental results show that our method is also effective and efficient. And finally, that's all. Thanks.